Hello, everyone. This is Tim Forty. My name is Abdul Kazim Shambra, and with me is my colleague, Daniel Vesego. Our team mentor for this project is Joseph Conan. Our project is on unsupervised scene detection on anime using Beta VAE. Scene detection plays an important role in assisting animators to create media content with smoother transition and improved frame rate. More so, companies such as YouTube will find this invaluable in ensuring that ads get added in between major transition. A more intuitive application of scene change would be in the area of CCTV surveillance, where a major scene change marks an aberration and should throw a warning signal. A clip with scene change apply will provide timestamps of all major scene changes, thereby saving human reviewers a tremendous amount of time that would have been expended in scanning through the entire clip. The baseline model central to this project consists of the Beta VAE architecture proposed by Higgins. The model is composed of two parts: an inference network which maps samples from a data set into a latent variable Z, and a generative model that decodes the latent variable back into the original data space. This paper demonstrates that disentanglement can be achieved by making a simple modification to the Beta VAE learning objective. The main idea is quite simple. In the standard VAE, an isotropic Gaussian is typically assumed as the prior distribution of Z. Thus, to encourage independence, the KL divergence of the term in the elbow is outweighed by a factor of beta. The following figure obtained from the original Higgins paper compares the output of the Beta VAE to the regular VAE model. Although the Beta VAE produces a slightly blurrier image than the VAE, the model scores an outstanding 99.23% in the disentanglement metric score used by the original paper, and only second to the DCIGN. And that's why the Beta VAE is chosen for this project. Since our project is about scene change detection, our focus is on how good our model is at capturing the rich latent features in the data.
So thank you, Shamba. Let's go through a scene change example. As you can see, when we go from frame AX to frame B1, there's a scene change. And also when we go from frame B7 to frame C1, there's a scene change. And finally, when we go from frame C6 to frame DZ, there's a scene change. So our project tries to find these frames where scene change happens. It is from Kimi no Nawa dataset. We have 142 pixel unique frame image. The total size is around 4.57 GB, and the average image size is around 40 kilobyte. So in the forward propagation, we have the image. We resize the image to 64 by 64. We convert it to tensor, we normalize it, and feed that to our encoder. After feeding that to our encoder, the encoder passes through a series of convolutional neural networks and finally through a linear layer to give us the mean and the variance. After getting the mean and the variance, we sample from the mean and the variance, and also by adding a unit Gaussian distribution noise. After that, we get our Z. After getting our Z, we'll try to reconstruct our image by passing it through the decoder and getting back the reconstructed image again. So this is the print of the model. For this project, we're trying to identify the frames where scene change happens. To do that, we feed consecutive frames to our model and get the Z embeddings. After getting the Z embeddings, we calculate the top KKL divergence between the Z embeddings. And we assume that the top KKL divergence between the Z embeddings are where scene change happens. To evaluate our model, we have a manually labeled validation data, and then our evaluation metric is going to be by taking the number of correct scene changes and dividing them by 100. We trained 5 different models with beta values 0.25, 0.5, 1, 2, and 4. And we select the best beta value after calculating the accuracy. These are the plots that we have got. And as you can see, we have the KL divergence loss, the reconstruction loss, and the total loss. Here are the performance results, and as you can see, the beta value of 4 gave us the best accuracy, and it seems like the lower the KL divergence, the better the model.
So far, we've discussed our motivation for implementing this project and how scene change detection can be applied in areas of industry. Also, we intimate our listeners on how Beta VAE captures rich latent features in our data. In addition, we tried applying quantization to the baseline model to compare any improvement in terms of model size, compute time, and performance. Our motivation for applying quantization is simply that deep learning techniques are compute intensive. For example, applying quantization to the ResNet architecture increased the inference time by a factor of 2 and with only a 0.2 drop in accuracy. These results are fascinating in the sense that not only can we now save our model in 4 times less storage, we can now run faster inference on low compute device. It is worthy to state here that at the moment, Python does not provide quantized operation on CUDA. In future works, it will be delightful to see quantization and CUDA in operation. Thank you for listening.